Just want to give us a quick introduction to today's lab, which is number 24, interference. So what we're doing in this lab is we have a monochromatic source of light, which means it's all the same wavelength. The light is coming through a slit here, just disappeared, and it's falling on a diffraction grating. A diffraction grating is a small piece of glass with lines etched onto it. So it's like you have a whole bunch of slits. So you are looking at the slit, the first slit, through each of the, you're looking at the light that came through the first slit, through each of these slits. And there are lots and lots of them, maybe 300 for each millimeter, okay? So consider these 5 slits. And if you follow the pink lines, they all actually will interfere constructively at this point on this screen, n equals 1, if there is a whole number of wavelengths difference, path difference between them. So in this case, I've drawn it so that each of these pink lines has a 1 wavelength difference in path between them. And I've drawn the green ones so that they have a 2 wavelengths path difference between them. So the green ones then will meet up here at n equals 2, and also you'd have an n equals 2 slit up here, and then an n equals 3, and an n equals 3. So you get an image of the slits at each of these locations. And so we are going to look through this and take a measurement of this distance, x, of each of these images from the central slit here, right? So it's probably not too hard for the first 2 gratings. The third grating, which I think you've got the 300 lines per millimeter, it's usually very difficult to get the third slit to see it easily or measure it. So the data may not be so great for that one. Okay, so what are we going to do with this? Well, so each of these, we find the angle theta that it makes, coming back to here and then here, right? So each of these makes an angle theta. And this theta, we can say, is then x, the tangent of theta is x, divided by d, where d is the distance of the screen from the grating. We call that big D. So then we have that tan theta is x over d. Let's see what else theta is, though. So theta is actually, if you look at the distance between any 2 rays, it's this little bit here, where this angle is theta. And then the distance between these 2 slits here is little d. So the path difference is d times the sine of theta. And sine theta has to be n times the wavelength, a whole number of wavelengths. We're using 1, 2, and 3. Okay, so we need sine theta, but we have tan theta. So that's fine. We can figure out what theta is by taking the arctan of this. That will give us theta. And then once we know theta, we can also figure out sine theta. We don't need to worry about transferring into degrees or anything here, because Excel works with radians, and we just keep this in radians. A hint to make sure you're doing it right is that sine theta, tan theta, and theta are almost the same when the angle is very, very tiny, as it is here. So they should all have roughly the same value. To find the uncertainty, you do the high value of this, x plus delta x over d, minus the low value, x minus delta x over d, and divide that by 2. That'll give you your uncertainty in each case. Right, so to remember, what you're trying to find is lambda, so you just take d sine theta divided by n. Don't forget to divide by n. Remember, you're going to need dollar signs in some of your formulas. And you should be able to check that lambda is pretty close to the given value for your monochromatic source using this analysis. Okay?